Hello, welcome to another problem session. Today we have a pretty standard problem, but we need to discuss some concepts here along the way. So here are two charges. They have a equal magnitude but the opposite sign, and they're placed in this manner. And there is some arbitrary point P. We want to know electric potential and electric field by them. So first thing to notice is finding electric potential. So if I know V at arbitrary point x, y, z, so this is the potential, then E at x, y, z, so we're talking about static E field. Right, so a static situation, charges are not moving, so static charges. So in that situation, we just have E is going to minus, I need to do this gradient of V. What is this? This just minus I hat dV dx plus J hat dV dy plus k hat dv dz. So these are just derivatives in the three directions. And if you do, there are similar things in say spherical coordinates and polar coordinate or cylindrical coordinates. Okay, so this is similar thing, you can look it up. Okay, so when we get there, we'll look it up. Okay, so what do I let's see, we would want to write V, and it seems like this would be a nice spherical coordinate to set up. So if you make the origin here, and this is the x-axis, maybe this y-axis, and maybe this is x-axis, and this is the z-axis, so they'll have a right-handed coordinate system, right? So if you project on the xy plane, then this distance, you can call it S for the cylindrical radial distance, and this angle we call it phi. But you know there's nothing will depend on phi. But anyway, we use this radial coordinate. So how do I get 1? 1 is just basically superposition. Use superposition. So electric potential from here plus electric potential from here, that should be the answer. So from here to here, let's call the distance r plus. From here to here, let's call the distance r minus. And we just need to figure out r plus r minus. So we'll have a V at P, which is function of r and theta. This won't be dependent on phi, okay? R and theta, so this would be 1 over 4 pi epsilon naught q over r plus 1 over 4 pi epsilon naught minus q over r minus. So that will be the answer. So how do we get r plus? R plus will be like, look at this triangle. This side is d over 2. This side is r. And this is theta, and this is r plus. So law of cosine can apply, and that just gives me r plus equal to square root of square r square plus d over 2 square minus 2r times d over 2 cosine theta. you can see if theta was 0, then it's just going to be r minus d over 2, right? And if theta is pi, then it's going to be bigger. So this minus sign works out fine. R minus will be square root of, let's see what that turns out. This is r, and this is pi minus theta, and this is r minus and d over 2. So this is r square plus d over 2 square minus 2r d over 2 cosine pi minus theta. So if you expand this, so this thing just becomes cosine pi cosine theta plus sine pi sine theta, and this is 0 and this is minus 1. So this whole thing makes a plus, so this whole thing is a plus 2 times r d over 2 cosine theta. So we got a, so the answer, by putting in there, we have the answer. Okay, so this is in a spherical coordinate, so we're done with one for electric potential. So how do I get the electric field? So electric field at P will simply be minus del the V r theta phi. So these are spherical coordinates. So we can go and look up what the del in a spherical coordinate look like. If you remember it, that's great. If you don't remember, you can just look it up. So here's a Wikipedia page for I just looked into del in a spherical coordinate, and so is the gradient where you have f, I have a v. So this is what it looks like. So there is a this direction, and this direction. You have to know what those directions are. And then it's not so, this one looks like a ddx kind of thing, but this does not look like ddx kind of thing, but there, it is in a way ddx, but this is ddx in the phi direction. So you need, if you haven't learned this, that's okay, we can just use this. Okay, now this guy will be 0, right, because we are don't have phi in our v, so we just need these two guys. Okay, let's go back to our drawing. So this would be simply minus dr, but the unit vector along the radial direction. So that's straight from here, that's the u hat r direction, and then you have a v, and so that's this guy, we'll take it with that, plus u hat theta, and then 1 over r dv d theta plus 0. We don't need to include phi because there's not phi here. So what is this direction? This direction is going to be, if I use this as a let's draw another ink. So we have a great circle here, goes from the North Pole to the South Pole, going through the point P. The direction in which theta is increasing is this direction. So this is 90 degrees to that, and this is u hat theta direction. And so it's not very difficult to do these derivatives, right, in multiplying. So let's do just this guy and see what it'll turn out to be. Okay, I'm going to erase something and calculate this. Okay, so can be a tedious calculation, but let's see if I were to get a little bit more space over here. So we can do this calculation. So when we go over here, we're going to find something here and something here. So basically you need to do del of this. So ddr of say r plus, we will need plus will be this quantity, so it will be 1/2 r plus square root, and then I go inside there, so this will be 2r, and this will give me 0, and this will give me this, for this goes away, minus d cosine theta. So it's not that hard, right? When I do this guy, so this becomes plus, everything's same, but when I have plus I get a minus here. So if I have a minus here, so if we have minus here, this will be plus. So we got both of these guys. So if I had this term dv dr, that will be q over 4 pi epsilon naught common, take a derivative of this, is minus 1/r plus square, and then dr plus over dr from this, and from this will be, there's a minus already here, and then minus 1/r minus square, dr minus over dr. And so we have got these guys come in here, and it's not that complicated, but looks, this r plus with this r plus can become r plus cube, 1/r plus cube, and inside is 2r minus d cosine theta, and this is already plus, so we'll have a 1 plus r plus cube, r minus cube, I mean r minus cube 2r plus d cosine theta. Now they don't combine because r plus and r minus are not equal to each other. So we got this term. We can do the similar thing for d theta, just the only thing will be over here. So 1/r is common, so dr plus d theta, and there will be r minus d theta, so it will be just 1/2r plus for the square root, and then if I go inside, this gives me 0, this gives 0, this gives me minus r, and this becomes sine theta minus. Now if I work out with a minus, then this will become minus, and then I just put in there and everything is hunky-dory, right? Okay, so that's that tells you the answer, okay, how to get to the answer. I wanted to talk to you about this part, okay? So when you have two charges like that and physically separate like that, we call it physical dipole. Physical dipole have the identity of the charges. The charges are separated, okay, and known to have a meaningful separation. Okay, we often deal with electric dipoles in situations where the charge is separated at the molecular level, but the distance at which we want the electric potential is a long distance. So we are interested, so if separation is in molecular level, but R we want is maybe lab level. Okay, so there's several orders of magnitude difference here. The molecular level will be like 10 to the minus 6 micrometer. Okay, and 10 to the 9 nanometers, a few nanometers to the 10 to the minus 8, and this will be like a few centimeters, so 10 to the minus 2 meter. It's like a 7. So you have a 6 order magnitude here. In this case, we are interested in something else. We are interested in Q times the separation distance is. So this as a product, we're interested in this as a product. And so when we expand this, we can express V at P. So this is also a function of Q, right? V is a function of Q and separation inside there, and at point R theta phi. So this is a full dependence. So instead of this, we want V at P a function of a Q times D, and maybe it depends on D, but Q has to be written in the as a combination of QD R theta phi. And this QD, how do we think of this? This QD as a new quantity. We call it electric dipole moment. And so let me erase and discuss a little bit more. Okay. Okay, so I'll just summarize something. When you have physical, the one that we got the answer here, this answer, this physical, what you have is a function of Q and R, Q and D, and R and theta and things like that, right? Now, if you replace it with this quantity, instead of Q, you want to define a new quantity, take one of these charges and multiply by the distance between them. Then you can replace the Q by P, but you won't be completely able to replace it, right? You replace it and the D will still be left. So the way you do it is take the Q and replace by this thing, and then this QD here you just write as P, and then the rest of the stuff you can combine the rest of the stuff as some D over R variable. R is fixed, so we can take D is very small and R is large. It is much less than 1 over here. So this is called mathematical limit, but it's not the regular limit you take. This is, you try to take this limit, but actually you don't go to 0. You keep the leading terms. Like if I have a suppose I take this limit and I get V of P R theta phi, so I get proportional to some times D over R. Doesn't mean this goes to 0. We don't set to 0. No, we stop this step. We keep it like that. But if I have 1 plus some C D over R, then we this is like a correction to some constant, and often we we can keep it, but here we'll find that this is more like that, more like this, not like that. So the leading term will be 0, so we will not have this term, will be like this over here. And of course you can, when you're taking the when you're doing this, we use a small element, like d over r is small. So let's work this out in the next section. And for some of you that can be a little bit advanced, so this will be the end of your idea about how to solve problems of electric potential and electric field for a physical dipole. So this one is more mathematical, and so I'm gonna work it out and talk to you next. Okay, so I worked out the ideal dipole. Earlier we talked about physical dipole with the d's were not there. So what we do is replace q by qd over d. So that's what it is. I did qd over d, and then I distributed the d's in the two terms. Our plus minus are like this. So I do this and do this, and then so if this is written as a p now, so the q is replaced by qd, which is p. Yeah, I'm having like a recording trouble right now. So so this from the previous earlier we worked out. So we want to expand this and this in powers of d over r. So there's several ways of doing it. One way is to convert every d. So convert d to d over r. How do I do? I said d is d over r times r. That will convert every d to d over r. So that's what I did over here. So this d is this stuff. And then when you pull r square out of this square root, this r comes out, and then the natural d over r becomes everything by d over r. So we can write epsilon equals to d over r now, and then we get this term. It's all equality. Now this term here, now this is, I can't do anything with the no Taylor expansion there, so we will do Taylor expansion like this part Taylor expansion, and then you can see that if I had a dr minus, this is the dr plus, and if I had a dr minus, I'll get exactly same thing but plus. And over here you have a 1 over dr plus minus 1 over dr minus. So there's a minus here. So bring it here. This one cancels out, and these two add, and the epsilon kind of cancels. So in the limit, epsilon go to 0. This will all go to 0. This will go to 0 as epsilon goes to 0. And this will be the leading term. So I use this with 4 pi epsilon naught. I see it's 4 pi epsilon naught missing here. 4 pi epsilon naught missing here. So this will be the answer for the dipole potential. And of course you can do electric field. You can just do del V, and these guys are spherical coordinates. You do a spherical coordinate. Okay, so you get the answer for it, and I will leave it to you. Do this out in a spherical coordinate. You can also write in a little bit more sophisticated way. If you think about P as a vector, go from the negative to the positive this direction, and this is the vector along the u hat r direction, the radial direction. So the angle between them is just, this vector and this unit vector. You can see P dot u hat is simply P times P vector u hat vector r vector, and then the angle between the cosine theta, and this is 1, and this is just p. So p cosine theta is just that. This sometimes people write it in an abstract way, but this is sufficient for our problem here. And then with this derivative taking, you should be able to complete this problem. Okay. Don't forget to subscribe, and if you like this kind of explanation, hit the like button. You can check out more discussion in the physicsbootcamp.org. Okay, talk to you later. Bye.